It's the 7A power functions. Oh, what happened there? The things that I talked about, I said that the things that to pay attention to is if you have an even power or you have an odd power. Even power is one of the things we know, is every time we square, or to the power of 4, to the power of 6, to the power of 8, it's always going to be symmetrical. Because you can't have negative powers. Like every time you square, it becomes positive. That's why you end up sort of a symmetrical look. Whether x is negative or positive doesn't matter. Negative 1 squared or 1 squared or negative 1 squared is the same thing. That's why you get the same y values. Whereas when you have odd powers, it's asymmetrical. Okay, it's same values. If you have 3 cubed versus negative 3 cubed, it's the same value. It's still 27, but it's a different direction. One's positive, one's negative. So you get this asymmetrical look, but it's the same value. And on this side here, this is same value, same direction. That's why they end up symmetrical. Okay, so that's what we know about even powers and odd powers. And then we go to negative, even, negative, odd. So let's say I have 1 on x squared versus 1 on x cubed. Same thing on a logical sense. 1 divided by the only thing that you can't have is 0. That's why you have an asymptote for both. Okay? But the difference in terms of the shape, same thing again, symmetrical versus asymmetrical. Every time you square, doesn't matter whether it's negative, it becomes positive. That's why the y values are the same as symmetrical. Whereas cubed, you can have the same values, but it's a different direction. That's why you get this asymmetrical look. Okay, so that means if I have 1 on x to the power 4, it's likely to look something like this. If I have 1 on x to the power 7, it's likely to look something like this. Okay, it's when you combine this, and you got to think about that. These are your properties. So if I gave you one, x to the power of 3/7. See, that logic is the same thing as saying x to the power 1/7, which you know what looks like, all to the power 3, because that's what it means. 3 cubed, 3 times 1/7 is what you have. So you can picture this graph with your domain being all real values except 0, cube every value. So what happens when you cube it? Your y values just become cubed. Okay, it gets larger. That's it. Okay, so you can break that up, you can predict what it looks like. And I showed you as you increase, which I'll show in Geogebra later, as you increase it to 4, to 5, to 6, and eventually you get to 7, x to the power 7 becomes a nice straight line. Okay, and then you increase, then you go, well, what happens when you have 8? What happens when you have your 9? And you start thinking about the values and you look at the graphs. That's what I want you to do to be able to analyze the functions is the goal of this exercise. Okay, the goal is to know the properties and then try to predict what it should look like based on the properties. Okay, and then you get your rational powers. You get your rational powers. So you had x to the power of 2. Okay, they're all positive numbers. It's a whole number. It's either 2, negative 2, 3, negative 3. Here you now have. I think so. Anyway, so x to the power of 3rd. You know, I just realized that's recorded on this thing. X to the power of 1/3, and you have x to the power of half. So with your rational powers, one of the things we know is x to the power of half is a square root function. You can't square root a negative number. That's why you have no negatives here. Whereas over here, you have x to the power 1/3. You can cube root a negative number. That's why you have negative values. And it's important because if I gave you, I can't remember which example I gave in the previous session, where you could either take out one of the two. You can either write it as x to the power of half, let's say to the power 7. Is it 7? Or you can write it out as x to the power 7 square root. They're both technically the same thing. True? But I told you that there is only one of the answers that's possible right now because one of it has a restriction. See, this one has a restriction. This one's saying that x can only be greater than or equal to 0 because you can't have any negative values. Okay, so this graph here would look like this. Square root, and then to the power 7 means all the values get to the power 7. Whereas over here, x to the power 7 can include negatives. That's why it's different. See, this one can include negatives, and then now you square root that, it gets smaller, right? But you can't say this and this are the same because this one's saying that you can have negative values, This one doesn't. So which one do you take? That one, because this one has no assumptions to it. It's just x is all real. This one has an assumption. Yep.
Does that mean that you could have, like, if an x to the power of certain value was negative,
yep.
Then after that, once you square root it, you get nothing for all the negative ones because you can't square root negatives.
Yes, you're right. So this would definitely have, so in order for this to exist, this is a composite function where it doesn't exist. So this one, you wouldn't be able to sketch it. If you sketch it in your calculator, they would do this one because this works.
Yeah.
This one you can, but this can't exist unless you put a domain restriction to it. But if you sort of write it, this is technically what you're trying to do, but you can't do that. And you're right, you can't square root negative values. So this would be an undefined function, doesn't exist, whereas this one could be defined that. This is called an implicit domain. Yeah, so you have an implicit domain where for it to work out, x has to be greater than or equal to 0. So when you type in your calculator, this is what it will look like, whereas this is what it should look like, but it isn't without the restrictions. Yeah. Okay. All right. So let's play around with tricky types now. So that's what I was talking about with the negative powers. All right, let's play around with GeoGebra, and you can look at all this again, but what I'm really trying to get you to do is not to memorize what each one looks like. What I want you to do is to be able to look at each power and say, well, what happens when I have a fraction, negative, and then if it's odd powered, even powered. Yeah, so I'm going to play with GeoGebra. I'm going to get you to think about it. It's up on Schoology, all the files right now, it's up there. I want you to, in your own time, play around, or use your calculator, play around with the powers, try to understand it rather than trying to memorize it, because that helps you analyze functions when you're doing exam 1 or exam 2. Okay? Let's have a look. Let's play with some of the GeoGebra. All right, you 12s. Okay. I'll just explain this and then we'll. Yeah. All right, you 12s, listening. Boys, thank you. All right, here we go. We all know the same powers. If you have x to the power of 1, straight line, pretty straightforward. When I change it to x to the power of 2, which actually I'll take the equation out so you can see, and I'll enlarge it. Blue, text. Okay, here we go. These are the ones you know. Shh. These are the ones you know. So I'll take away the red. As I increase b, these are the ones you know. So it's 3, asymmetrical, even, positive 4, positive 5, positive 6, positive 7, positive 8, positive 9. So they're all predictable in terms of your integers. Quick and easy, yeah? Then we go to your negatives. You got your negative 1. Okay, that's a 1 on x function, so it's a hyperbola, it's asymmetrical, makes sense. Then if you square it, so 1 on negative 2, it should be a truncus. It's true. Then if I go to 1 on x to the power of 3, it makes sense. Odd powered, asymmetrical. Thank you. 1 on x to the power of 3. So this is exactly the same thing as writing. It's always about thinking about your original function, what you know, and try to rewrite it. So I technically have 1 on x, or think about it as x to the power of negative 1 to the power of 3. That's what that negative 3 is the same thing as. So if you know what this graph looks like, you can say 2 to the power of 3 just multiplies itself 3 times. That's why it gets larger. That's why you know the shape. You just know it's a bit larger. Okay? So same thing if I had increased it to x to the power of negative 5, you should expect that it should still be the same. So it's only getting larger. The values are just getting larger and larger. The y values are getting super large, and in between should be getting much smaller. That's it. It's getting smaller and smaller and smaller, and getting larger and larger and larger. That's all you're doing. So it's just x to the power of negative 1 all to the power of 5. That's what you're doing. That's why it's easy to predict. Even if I gave you x to the power of negative 7, I would predict that it'd still be asymmetrical. So 7, still asymmetrical. Move to A9. Still asymmetrical. But you can see it's getting more and more square because it's getting larger and larger and larger much quicker, so it looks much steeper. Yeah? Whereas if I put it all the way back to -1, it's wider. It makes sense, because when you cube any values less than that, of course it gets really small. So they get small, and it gets larger and larger quicker. Okay? So that's why once you know what -1 is, and you know what -2 is, you can predict for -2, -4, -6, -8, -10. They all look the same. So all truncus will all be truncus. All hyperbolas will be a dilation of the hyperbolas. Yeah? So we got our positive integers. Now I want you to look at rational, so fractions. Okay, so fractions, let's have a look at a fraction one. If I change, I think it's C. C? No, not C. It is C. Oh, it's the purple one. Okay, not purple. Purple. All right, here we go. Take away the green. First one you know is the square root function when it's 1 on 2. Square root function. Makes sense. Only positive x values. Then I go to cube root. Cube root, we know that you can cube root negative values. So if I increase it to 3, it makes sense. 1 out of 3, we can have negative. But it's the same values. See, if you cube root 27 or cube root -27, it's still going to give you a -3. It's the same thing. Okay, so that's why it's the same shape, but it's just a different direction. Whereas the square root function couldn't take any of that. So what happens when I do x to the power of -1/4? Sorry, 1/4. If I change to 4, that's the square root function. Just squaring them. So if you think about it, x to the power of 1/4 is like saying x to the power of half and square rooting that. That's what you're really doing. See, power of 1/4 is like saying square root function and square root that again. So of course it's smaller. Okay, it's flatter, it's smaller. It makes sense. So to get a quarter, it would have to be like this. If I did x to the power of 1/5, see 1/5, it's still the same thing. You're just taking your 1/3 and you're making it the 1/5. Of course it's getting smaller and smaller. That's all you're doing. Okay, so that's what I mean by every time you're changing these values, that's what I want you to keep thinking about. How do you do that? Yeah? Now here's the thing I want you to look at. So we've got positive values, we've got negative values, we know our square roots and cube roots, and fourth roots and fifth roots, yeah? Now I want you to think about what happens when you increase the numerator. Okay, so the numerator, you have 1/4. What happens when I increase it to 2/4, 3/4, 4/4, 5/4? So let's have a look. I want to change the values here. I'm going to change that. So here we go. 1/4. 1/4. 2/4. Okay, so 2/4 makes sense. You're just squaring them. So think about it. This is 1/4. Squaring it. 2/4. Cubing it. 3/4. Whoops. 3/4. You're just cubing it, so it gets larger. It makes sense. Okay? And then 4/4 makes sense that you get a straight line. 4 out of 4 is 1, so x to the power of 1. Yeah, so if I just write it out again, see, each one, x to the power of 1/4, you knew was like a square root function. Then an x to the power of 2/4 is the same thing as running x to the power of 1/4 squared. So if you squared, obviously all the y values get squared. So that's why it was getting larger and larger. If you want to work out what x to the power of 3/4 is, x to the power of 3/4, that's the same thing as saying x to the power of 1/4 cubed. So if you're cubing it, it gets larger. And then finally, x to the power of 4/4, that's the same thing as writing x to the power of 1. That's why it's a straight line. So if you want to know what x to the power of 5/4 is, okay, that's the same thing as saying x to the power of 1/4 to the power of 5. But there is a point, if this is your straight line, then obviously if you're cubing it, if you're making it to the power of 5, it's going to be larger than this. So it's going to curve in that direction, it's moving more towards your y values. Yeah? Because it makes sense, you're increasing it past this sort of straight line here. So of course it's going to get a bit larger. So what you'll see is if you increase it to 5, so if I increase it to 5 now, it curves. And it's curving towards your y-axis. So if I increase it to 6, It's moving closer to your y-axis. If I increase it to 7, it's getting closer and closer, but look at when you get to 8. It makes sense. 8 divided by 4 is 2. X squared. So you get your x squared graph. And then you go to your 9, and it goes on. So that's what I want you to be able to analyze for each one. Now, what's the problem with this one? What's the problem with this graph? There's an issue with how I was teaching you the whole time. What's the issue? What's the issue with x to the power of 8 on 4? Yes, you can reduce it to x squared. It's like saying this. One of the questions my uni friends were asking me, and they couldn't figure out why this is the case, and I said it's because they haven't done methods for a while. But the question in their exam was like this. And they said this can be simple, this is equal to x. And they said, prove that this is wrong. For what values? And they said this should be all fine. Now they had A, B, C, and D. What's wrong with what I just did? X squared on x. If I gave you f of x equals to x squared on x versus g of x equals to x, are they both the same graphs? Because that's what the question was asking, the uni question.
X can't equal 0?
Yes. And that's the problem here. In both of them, yes, you can reduce x squared on x to x, but you can't say x squared on x is the same thing as x. Why? As you just said, when x is 0, it's undefined. This one is okay to have a 0. So they're both different graphs in that sense, that one will not include 0 and one will include 0. So why am I asking that question? It's the same thing with this one. The x to the power of 8 on 4, yes, you can simplify it down to x squared. But with x squared, that means you can have all values. But x to the power of 8 on 4, you can also think of it as x to the power of a quarter to the power of 8. What's the problem with that? You can only have positive, 0 to positive values. And having the 8 increases it, so you only have half of it. So in these kind of questions, you've got to be careful with the domain, which one will work. And that's why it lends itself nicely to 7b, composite functions. Composite functions make sure that the domain of this has to fit. The range of this has to fit the domain of x to the power of 8. That's what we were doing in chapter 1. Hopefully now it makes a bit more sense and logic for you there. Okay? But there you go. So if you can now figure it out, you can find out that straight line. You know, x squared will give you that, and it keeps moving this way. I can ask you any question now. I can say x to the power of, like 7 on 6. What it should look like. So you can picture, well, what does 7 x to the power of 1/6 look like? And then if you put it to the power of 7, what should it look like? Okay, that's the skill that I want you to take out from 7a. Not to memorize these properties, but I want you to think about it. Then the last question is, what happens if I put a negative now? So we haven't talked about negatives. What happens if I have a negative fraction? Negative half, for example. So let's have a look. Let's change it. Back to, this is 1. This is half. Let's go to negative 1. Negative 1 is x to the power of negative half, which is the same thing as writing x negative half is the same thing as writing 1 over square root of x. Why does it look like that? Someone explain to me. This is going back to implied domain and composite functions again. Why does it look like this? So x at negative half, it's 1 on root x. What do you know? It's all about analyzing the function. It's not about memorizing. Think about it. What can I have and what can't I have? It's going back to composite functions again. What can I have? Look at the functions. What are my restrictions? Can't have negative values. Why? Square root. Anytime you see a square root value, you know you can't have negative values. So of course, all the negatives are gone. Why do you have an asymptote? You can't have 0. It's just like your 1 on x function. You know that x, or the bottom denominator, can never be 0. So as soon as you have a square root, 1 it can't be negative, 2, you have an asymptote. So technically, if you took away the square root, you have a 1 on x function. Put a square root means take away that negative values. Square root means square root all the x values before you put it in, so it looks like you want an x, except it's only the first quadrant. Okay, that's what I mean. There's all these functions. I don't know them all. I just read the graphs. I just read the equation and then I predict what it looks like. So I don't memorize all this. I just look at it and I go, oh, well, what should it look like? Okay, that's what I want you to do as part of the exercise 7a. It's not about doing the exercise because they don't go into these kind of numbers, but I want you to think about it. That's your skill. Okay? Let's have another go and then I'll get you to do the exercises. What happens when I put -1 on 3? Let's have a think. If I have -1 on 3, okay, have a think about it and then, wait, is it this number? No, it's not that number, it's this one. Negative, whoop, no, actually. 1 on 3, what, there we go. Ah. Does that make sense? Why do we have this sort of shape? So think about it again. If you were to break it apart, x -1/3 is the same thing as writing 1 over x to the power of 1/3. X to the power of 1/3 is the same thing as saying 1 over cube root of x. So if you look at your equation, it's all about analyzing here. 1 over any function has the asymptotes. You always have a horizontal asymptote and a vertical asymptote because the denominator can't be 0. So that's why it looks like this. 2, cube root. Can you cube root negatives? Yes, you can. That's why you have the negative section. Can you have a positive? Yes, you can. That's why it carries the same thing. The only difference is when you cube root the value, it gets smaller versus a 1 on x function. So if I go back to the green, or is it red? Is it a red? Green, blue? Ah. I want you to look at the blue graph, 1 on x function. Why? How do I do it? I think I got to do the green. Was it 1? Sorry. What I want you to see, x to the power of -1 is the green function. X to the power of -1/3 is your purple function. See, the only difference between the two is one's cube root. So when you cube root the x values, of course, it gets larger first. You cube root these values, of course, it's larger after this point. Yeah? That's what I want you to be able to analyze. So think about what happens when you use the power 4, -2/4. That's what I want you to think about. Okay? It's not about memorizing them, it's about analyzing those functions, what you know, what you don't know. Okay? Alright, have a go with exercise 7a. That's what I want you to do for the first half of the session, and then we'll do composite functions, which lends itself to this again. Okay? There you go. Don't memorize. You can play around with all these and predict all of them, because the textbooks are real easy. 3 over 2, 2 over 3, really straightforward. Simple and easy, yeah? The skill is to analyze. Don't memorize. Here we go. I'll put up the questions. Just try those. Have a predict. What does -1/4 look like? What does -1/5 look like? 3/5, 2/5, by 3. These are just values, but think about it in terms of the values. What does each of these graphs look like? That's what I want you to try. Let's go.